Imagine a night that never ends. No sunrise, no warm horizon, only a slow river of stars. This is a rogue planet, a world drifting free, no parent sun, no familiar seasons. Tonight we take our time. We will ask simple questions and follow them patiently. What is a rogue planet? How does a planet lose a star? Could such a world stay warm and even hide an ocean under ice? And if life loves to adapt, could anything live there at all? Settle in, breathe slowly, let the sky be quiet. What is a rogue planet? A rogue planet is a planet that is not bound to a star. It moves through the galaxy on its own path. Some are tossed out of young solar systems. Others may form far from any star, inside dark clouds of gas and dust. The word free-floating is common. So is interstellar planet. All mean the same idea. A planet without a sun. You can picture the scale. Our galaxy is wide and deep. Between the stars lies a soft, dark ocean. Rogue worlds travel that ocean in long, cold arcs. We do not see them directly very often. They are faint. They do not reflect a host star's light, but there are ways to catch them in passing. In a young system, the rules are simple. Gravity keeps score. Disks of gas thin out. Newborn planets tug at each other, and the ledger of momentum must balance. One close pass between giants is enough. Energy trades hands. One world falls inward and calms down. The other is flung outward, eccentricity rising until the escape speed is quietly crossed. This is planet-to-planet scattering, the most common road to exile. Sometimes the push is gentler. While the disk still exists, planets migrate through it. Chains of resonances form 1 to 2, 2 to 3, neat little ratios. When the gas disperses or a resonance is crossed at the wrong time, the chain destabilizes and the same story unfolds. Close encounters, scattering, ejection. There are more elaborate paths. With a distant, tilted companion, another planet or a second star, Kozai-Leadoff cycles can slowly pump a planet's eccentricity. Periastron dips inward, apastron swings far out, and one rude meeting later, the planet is free in a crowded stellar nursery. Even a flyby of a neighboring star can torque an outer planet enough to unbind it, and very late in life, when a star swells and loses mass, its grip weakens, outer orbits expand, and the loosest members slip away. Not every drifter is thrown out. Some are born cold. Turbulent fragments of a molecular cloud can collapse directly into planetary mass objects that never ignite fusion on the low end of the brown dwarf border. They glow faintly with leftover heat, then fade. Can a sunless world stay warm? At the surface, darkness wins fast, but planets have interiors, and interiors remember. There is primordial heat, energy locked in during formation, and radiogenic heat from the decay of uranium, thorium, and potassium. On Earth, the average outward flow is about 0.08 watts per square meter. Scale up the mass and radiogenic budget, and a super-Earth leaks more. Over billions of years, that slow trickle keeps rock warm and water interesting. If the ejected planet keeps a thick hydrogen-rich atmosphere, tens to hundreds of bars, the air itself becomes a blanket. Hydrogen's collision-induced absorption makes a surprisingly strong greenhouse even without sunlight. With enough pressure, the planet's maximum outgoing heat rises. Surface temperatures can sit above the melting point of water. Without a host star blasting EUV, atmospheric escape is slower. The main thief is thermal escape rather than photo-evaporation. High mass helps, so does a magnetic field. If the planet carries a large moon, slow flexing can convert orbital motion into tidal heat, the same physics that keeps Io molten but writ on a darker stage. And if the ocean is trapped beneath ice, pressure phases of ice can appear at depth with a layer of liquid between them. Ocean above, high pressure ice below, rock at the base where hydrothermal reactions feed chemistry. Surface habitability is unlikely unless the air is extraordinarily thick, but subsurface oceans are the conservative, durable outcome. Liquid water sealed under ice, warmed from within, stable on geologic time. So then, could life survive in the dark? Where sunlight fails, chemistry can still pay the bills. On Earth, microbes thrive around hydrothermal vents using chemolitho-autotrophy, oxidizing hydrogen, hydrogen sulfide, ferrous iron, and methane to build biomass. Water-rock reactions such as serpentinization naturally produce hydrogen and gradients to harvest. Even radiolysis, radioactive decay, splitting water into reactive pieces, can drip feed energy into an ecosystem. The constraints are strict. Energy flux is low, so metabolisms are slow and communities small. Nutrients depend on continued water-rock contact to refresh redox couples. But the clock is generous. If heat flow persists for 100 million to 1 billion years, an ocean has time to explore many micro-solutions. Complex multicellularity is less favored. Low energy and environmental stability slow evolutionary experiments, but a layered microbial ocean is physically reasonable. If such biospheres exist, they hide well. No reflected light, no pigment forests, just faint chemistry under ice, far between stars. How we might find them? Microlensing is the workhorse. When a dark foreground mass passes in front of a background star, gravity magnifies the starlight for a short time. The event's timescale scales roughly with the square root of the lens mass. Hours for Earth-like masses, days for Jupiter-like. There is no repeat. The light curve rises and falls, and the sky forgets unless you were watching. High-cadence surveys, staring at crowded star fields, collect these whispers. Parallax and finite source effects help estimate mass and distance. Thermal emission is the second path. Young or massive rogues still glow in the infrared. With sensitive instruments, especially at longer wavelengths, a handful have been picked out in nearby associations. As they cool, they slip beneath detection limits unless they're large. Other methods are possible but rare. A stellar occultation, a planet briefly blocking a star, would be unmistakable and very difficult to catch on purpose. Astrometry gets no anchor without a host star, though high proper motion searches in the IR can net massive nearby candidates. The population story arrives statistically. Count microlensing events, fold in survey cadence and geometry, and solve backward for the space density and mass function. Our error bars are wide today, but each upgrade in cadence, field of view, and infrared sensitivity tightens them. Open questions remain. What fraction of drifters were born in disks and ejected versus born in clouds? How steep is the mass distribution below Neptune? Can a super-Earth realistically retain a hydrogen-rich atmosphere with surface pressures of at least 10 to 100 bar for billions of years, even without a host star? Or do non-thermal losses erode it faster than we think? After scattering, how often do large moons remain bound? Our models disagree, our observations are sparse at low mass and old age. But the broad outline is steady. Gravity builds systems. Dynamics edit them. Some planets keep their stars, some don't. In the dark between constellations, a quiet class of worlds moves on schedules longer than our species. If you look up from such an ocean, there is no dawn to wait for. Time is counted by the slow chemistry of stone and water. And yet, by the rules we already test in our own system, that ocean can stay liquid. It can host metabolism. It can last. For us, the task is patience and better eyes. Watch more stars more often. Listen in the infrared. Let statistics do the heavy lifting. And accept that some discoveries will come as brief brightenings we almost didn't see. Moments when a hidden mass bends starlight just enough to say, "I am here," and then is gone.